Welcome. In the last session, we looked at two examples. The first example was about trying to define speed. Speed at the moment doesn't make sense because you cannot have distance over time if the time is zero. But if you looked at the table of distance over time, as we make the time intervals shorter and shorter, but kept one of the endpoints at a specific number, in our example t equals 2, it looked like the speeds have some kind of limiting value, so to speak. So this is getting down further and further to 64. On this side, it's going further and further up. So it looks like this table should be completed by putting time t equals 2, average speed 64 for that particular moment. Our second example was trying to define the tangent. We actually tried to find the slope of the tangent. We also drew the straight line. We took the curve y equals x cubed and a specific point 1, 1 on it, looked at the slope of the line joining 1, 1 and x, x cubed. Of course, x has to be different from 1 for slope to make sense. But if you look at the table of the x values and the corresponding slopes, it looked like when x is 1, the slope should be 3. And of course, the straight lines looked like closer and closer to being the tangent to the graph, just barely touching the graph at the point 1, 1. In each example, we had a function. In the first one, it was 16t squared minus 64 over the quantity t minus 2. In the second example, it was x cubed minus 1 over x minus 1. This is not defined at the specific value of the variable we are interested in. In the first example, t equals 2, second x equals 1. And the original context didn't make sense either. But if you looked at the table of values, it seemed like we could assign a value at the missing point. So this is what the concept of limit was designed to do. So I have some function f, which we'll assume is defined for all numbers x near c, except possibly for c itself. So it doesn't matter what f does at c. Also, we are looking at functions for which it looks like there should be a value at c. By that we mean that if you look at the table of values of f, as x gets closer and closer to c, f of x gets closer and closer to some number L. In this case, we say that f of x approaches L as x approaches c, or that the limit as x approaches c of f of x equals L. I will write this either in this form. LIM is an abbreviation for limit. I read this as limit as x approaches c of f of x equals L. Sometimes I might simply say that f of x approaches L as x approaches c. Our two examples then can be summarized by saying that the limit as t approaches 2 of function 16t squared minus 64 over t minus 2 equals 64, and the limit as x approaches 1 of x cubed minus 1 over x minus 1 equals 3. So this is the basic intuitive idea of limits, and we need to refine this further. And we also need to know exactly what's involved in this, what we don't want to allow as limits in order to pin down the definition, pin down our idea. That's what we will do in the next few sessions. Goodbye for now.